So, thank you once again to everyone. So the final talk today will be by Udhav Fowdar. So very recently, until very recently, of the State University of Campinas in the state of Sao Paulo, and now at the University of Torino, and who will speak about flows of SU2 structures. So thanks very much, Udhav.
Thanks, Andrew, for the introduction, and thanks to the organizers for inviting me to give this talk here at IMPA. It's a pleasure to be back. So today I want to talk about geometric flows of SU2 structures. So it's a project that I started at some point last year, jointly with Enrique Saep, back when I was still a postdoc at Campinas, and I very recently moved at the beginning of this year to Torino. Okay, so this talk is sort of fairly elementary, and I hope everyone sort of can understand what's happening and what we want to do and where we're trying to get to. Okay, so let me sort of begin by telling you what the goal of this talk is. So the goal is, sort of morally speaking, to give a classification of second order geometric flows of SU2 structures, and I want to prove existence of a certain families of flows. Okay, so that's our main goal, and the plan for the talk is roughly as follows. So first, I want to give you some motivation on and some context for the problem, so why we're looking at this problem, what we hope to achieve. Then I'll get into the talk. I'll tell you what an SU2 structure is and how we would like to flow it. Then I'll tell you about the results we have at the moment and what we are still trying to do and what we would like to do next after this. Okay, so let me start from the beginning. So we already heard about Berger's classification in Robert's talk. So let me sort of remind you again in case you're not used to thinking about special holonomy. So back in the 50s, Berger classified Riemannian holonomy groups of manifolds which are not symmetric spaces and whose metric is not locally a product, and it falls into this small list below. I've omitted just the Riemannian case where you just have the metric as a parallel tensor. So in each of these cases, in addition to having the metric, which is covariantly constant with respect to the level shift connection, you have other set of tensors. Okay, so in the Kähler case, for instance, you have your Kähler form and you have the complex structure, which are both covariantly constant with respect to the level shift connection. Now, in all of these cases, you don't need to specify a metric. All you have to do is specify the underlying tensor, and you have to ask that this tensor is covariantly constant with respect to the level shift connection. That's because the stabilizer of these tensors under the action of GL and R is already H. So the stabilizer of this tensor is already sort of H. And so because H is a subgroup of SON, that means that the tensor alone will determine the metric. And once you have the metric, you can compute the level shift connection out of that. And then the question, the holonomy reduction problem, is equivalent to the PD that this tensor is covariantly constant. In this talk, whenever I write eta is going to be some sort of tuple from this list. So for instance, if I'm talking about Kähler manifold, eta would just be the pair omega and J. Okay, so from a PD point of view, this corresponds to a system of first order PD. Well, first order because there's only one derivative here. Nonlinear because the tensor determines the metric and the metric determines the level shift connection. And then I'm asking to solve this PD here. That's where the nonlinearity is coming from. And it's not one PD, it's a system of PDs. And the number of PDs depends on the dimension of the manifold, so lambda 1, and the complement of the holonomy algebra inside lambda 2. So remember, the holonomy group is a subgroup of SON. So as Lie algebra, the holonomy algebra sits inside the space of two forms, and the complement is precisely inside the space of two forms here. And in this talk, I would always like to think about the intrinsic torsion as a tensor, as a one form, which values in a certain subbundle in the space of two forms. So H-perp is just a complement of the holonomy algebra. And I would like to define it implicitly by this relation here. So here, diamond is simply the standard sort of endomorphism action. So you think of the torsion tensor as a one form. So once I feed in a vector, I get a two form. And I think of this two form as an endomorphism, and I can naturally act on my tensor eta. And this is precisely what I would like the current derivative to be. Okay, so that's what the intrinsic torsion is. And the Holonomy problem is simply asking that T here vanishes. And in this talk, I would like to sort of consider the problem of trying to find solutions to the Holonomy problem by means of geometric flows. By which I mean, I would like to start with my tensor, which is arguably sort of not covariantly constant, and I'd like to evolve it by some natural means and make it torsion-free, or something else. It doesn't matter. But the question is, what do I put there? So I would like to sort of motivate this problem from the perspective of G2 geometry. So we heard a little bit about G2 geometry this morning and in the previous talk. So let me sort of quickly remind you what it is. So a G2 structure on a 7 manifold is determined by an algebraically special freeform phi. So a generic freeform is going to have this property on a spin manifold. And this freeform will determine a Riemannian metric and also an orientation. And so once you have the metric, you have the Levi-Stricter connection, and you can ask when is this covariantly constant. And it turns out it is covariantly constant precisely when it is both closed and co-closed. And we like to.
Especially you need generic, right?
Yes. Well, yeah. In this case, yes. But that's just because its orbit is open. Yeah. Okay. So probably the most successful strategy in studying sort of geometric flows in the context of G2 geometry is the Laplacian flow, which was introduced by Robert in the early 2000s. So in this setup, what you do is you take your free form, phi, and you start by assuming that it's closed, and you evolve it by its Laplacian. And clearly, you can see that the critical point of this flow is precisely going to be those when the free form is harmonic. So on a compact manifold, that means it's both closed and co-closed. So it's naturally, by this equivalence here, it's covariantly constant. In fact, even if it's non-compact, that statement still holds true. Okay, so the existence and uniqueness for this flow was proved by Bryant and Xu in 2011. And the sort of analytical properties of this flow was really sort of developed by a series of papers by Jason Lotte and Yang Wei. I mean, not just one paper, but a set of papers, when they sort of found sheet-type estimates for the flow, compactness results, and showed that the torsion-free guys are stable. Like, if you're close enough to them, then you're going to flow back. And so a lot of things are known in this context. Okay, so we know plenty of examples and solitons and whatnot. Now, a few years after, well, quite a few years after, Karagiannis, Mackey, and Sui introduced the Laplacian coflow. They said, let's sort of try to mimic what Robert does, but instead of trying to evolve the free form, we're going to try to evolve the four form instead, so the Hodge dual. And just as before, we're going to impose that the four form is closed, and hopefully, if the flow exists, then this will give you critical points because would give you sort of torsion-free guys, because this guy here vanishing would mean that it is both closed and co-closed. But surprisingly enough, this flow, even till today, doesn't have existence. We don't know that this flow exists. Also, we have plenty of examples in the context of sort of Lie groups and homogeneous spaces, but that's just because in this setup, it's just an ODE problem. So in this case, you always have existence.
You don't have proof of existence, but you're not asserting that the flow doesn't exist, right?
Yeah, that's true. Yeah, we don't know, but yeah, that's just because the standard techniques don't work. Yep. Okay, so to sort of solve this problem, just a year later, Sergei Grigoryan introduced the modified Laplacian coflow. So what he did was he basically added some extra sort of second order term to the Laplacian coflow. And with this extra term added to it, he was just able to prove existence. So basically, once you add this term here, sort of the bad terms that sort of make the flow not parabolic in the right direction just happens to sort of vanish, and then you're able to sort of use basically the same ideas as in the Laplacian flow, and you're able to prove short-term existence for this flow. So while now we have short-term existence, the problem is now we don't know what the critical points are. I mean, of course, if you're torsion-free, surely you're a critical point of this guy because t vanishes, this guy here clearly vanishes, this guy here also will vanish. But what are the critical points in general? We don't know. So we've sacrificed existence at the expense of critical points. For instance, nearly parallel G2 manifolds would be critical points of this flow. Okay, so the story goes on, and people keep thinking about geometric flows. So in 2009, 3 different groups of people, so Dwivedi, Giannotti, Skaraganis, at the same time Sergei Grigoryan, and also Eric Lubo and Enrique Saeb, all came up with what is known today as a harmonic or isometric flow. So in this setup, what you do is you take your freeform, and you evolve it by the divergence of its torsion. So the divergence of its torsion is some 2 forms that values in H-pub, so in the complement of G2, so that's sort of just a vector field if you want, and then you can act on your freeform, and then this gives you a flow. So why is it called isometric? Well, it's called isometric because this flow doesn't change the metric at all. It's just sort of some sort of gauge fixing condition. So what it tries to do, basically, you take the L2 norm of the intrinsic torsion, you fix the metric, and you try to minimize this guy here. Okay, so you consider so G is fixed. So G fixed. So try to vary in isometric cause. Okay, so that's what they were all doing, and the paper appeared like an archive, like just weeks between each other. It's just an endomorphism action. Oh. Yes, yeah. So you feed in a vector, and yeah, just an endomorphism. I'm going to give an expression for that in a minute. Okay, so, but the key insight that Eric Lubo and Saeb had was that they were not interested in sort of just the G2 case. They were interested in the general case, and what they proved was basically that this isometric flow makes sense irrespective of what geometric structure you were using. So they were able to prove short-term existence of that. And maybe I should say, why is it called harmonic? The reason why it's called harmonic is because the way they prove sort of existence of this flow is by considering as some sort of a heat map flow. And then, so that's where the name harmonic comes from. Okay, so now, based from this, you can ask the question, well, given an H structure, what other flows could one have? Okay, so clearly, if you just try to do the Laplacian flows, that's not going to make any sense. So we'd like to come up with a nice way of sort of trying to find a geometric flow. Okay, so let me give you a general framework for that. Okay, so if you want to study sort of flows of H structures, so here's how you start. Suppose you have an endomorphism, which I'm going to think sort of as a 2 tensor A here. You can act by the endomorphism action, and this is the action. So it is sort of just sort of contraction and tensor product on the indices of any tensor alpha here. And I'm just going to divide by -2 just because in my notes I did that, but usually there's not a -2, just sort of normalizing fact. But with this sort of language, any flow of a general sort of H structure can be expressed in the following way, where A is any sort of tensor, and then you take the standard sort of endomorphism action on your tensor eta. So eta here is again as in, let's say, the Berger's list, okay? So I don't specify what eta has to be. And sort of, so why is this sort of the right thing to do? That's the way you should think about it is once I give you sort of an initial data, so I give you an initial tensor eta node, you can look at its GL in orbit. So it gives you some sort of submanifold, subvariety. And then what you'd like to do is you would like to flow only within the space. So in the G2 case, this is not really a problem because because a generic form is going to be a G2 form. So you can move in any direction you would like, that's fine. But if you have a specific H structure, you better move in a certain direction. And this is what this flow here isn't capturing. Okay, so that's why the endomorphism action. You're differentiating sort of a GLN action. Okay, so
by a general flow, you mean one of the previous ones, or like the most? I don't understand. What do you mean by a general flow?
Any flow. Any flow, because if you start with sort of some initial data, you like to move it, right? And then if you move it in any direction, it might just stop defining an H structure.
Well, this is a family of different types of flows, but the
yes.
question is saying, well, not all flows are in this form, right?
Yeah, potentially, yes. Yes.
All flow of H structures as H structures are to first order like this.
I'm just going to stick with these type of flows. Okay. I don't know any flows that's not of this type. Okay.
I think you mean this makes sense for a general flow.
Yes, this makes sense for a general flow. Yes.
The general infinitesimal definitions of an H structure as such are given by the body action.
Yeah.
That's what we mean.
Okay.
But, so, just
Oh,
to make
so-
sure we understand what you're saying. I mean, there's a divided by -2. Is that literally just a conventional factor of -1/2, or are you saying something symbolic?
No. I'm just doing that because in my notes I use this convention, so just for formula to make sense. No. I think it's a convention. There's no -2. Yes. That's just me because, yeah, I didn't use the standard convention when I did it. Okay. So let me just say something. So flows in the sort of general setup were sort of written in this language first, to the best of my knowledge, by Spiro Karagiannis when he was looking at flows of spin-7 structure. Yes.
Yeah, I'm just wondering why you have two indices down on A. I mean, GL and R should be.
Yes. I'm just assuming there's a metric around so I can just lower.
But there's no, you don't need a metric to define this.
Yes. That,
So it would be better to leave one of the indices up.
yeah, no. I agree.
It would be less confusing.
Yes.
That's true. But I'm always going to care about the case when you do have a metric around, so I'm just going to ignore. That's right. But yeah, you're absolutely right. Yeah, I think in the papers it's written, it's with sort of as endomorphism. Yes, yeah. Yes, that's my fault. Yes, that's my fault. I didn't find endomorphisms with 2 tensors. Yes, sorry. Yes, it's true. Okay, so note that if I had given you a skew-symmetric endomorphism and I took the standard endomorphism action, then because eta is stabilized by H, that means that the image will always lie in the complement of the H algebra. Okay, so because of this, I can restrict my tensors to simply the ones where the skew-symmetric part only lies in sort of H part. Okay, it's not in H. And what I would like to do is I would like to sort of consider flows just when H is equal to SU2 in this case. And then I'll sort of tell you what would a general strategy be. Okay, so let me get into the SU2 setup. Okay, so what is an SU2 structure? So an SU2 structure on a 4 manifold is given by a triple of non-degenerate 2 forms, omega 1, omega 2, omega 3. And this satisfies the fact that if you wedge them together, then you get sort of a multiple of the identity, so times the volume form, which I'm going to take omega 1, wedge omega 1. And it comes with a certain orientation, which means that when I hook a vector field x with omega 1 and the corresponding vector field y with omega 2, and I plug that into 3, I get a positive number. So that's barely saying that I have a triple, but they're oriented. Or equivalently, I'm just going to identify them at a point with the standard sort of self-dual one on R4. Okay, so once I give you a triple, you can cook up the almost complex structures by this expression here. So for instance, J1 can be cooked up using omega 2 and omega 3. And once you have the almost complex structures, you can define the metric out of this using this expression here. Okay, so everything is purely encoded using the 2 forms. So I'm just going to stick with the 2 forms from now on. Okay, and this set of data is called a hyperkähler manifold if the 2 forms are covariantly constant, or equivalently if they're all closed, in which case the metric is Ricci flat. And what we'd like to do is we'd like to find nice ways to sort of evolve the triple. That's our goal in this talk. Okay, so before that, let's look at the space of tensors on a 4 manifold. So whenever I give you a 4 manifold with an SU2 structure, well, since you have a metric, you can always split the space of 2 forms into self-dual and anti-self-dual form. And because I have an SU2 structure, I can sort of trivialize the space of self-dual 2 form, which I'm going to sort of trivialize by omega 1, omega 2, omega 3. And on the other hand, the space of symmetric 2 tensor, which always split into the metric and the traceless guy, can now be refined. So I can split the space of traceless symmetric 2 tensor as a type decomposition with respect to sort of J1, J2, and J3. And so for instance, S201 would be the set of sort of traceless symmetric 2 tensors on which J1 acts as identity, but J2 and J3 acts as -1. Okay. space of one form is irreducible, so is space of free form. So note that from sort of as SU2 modules, these spaces are all isomorphic because they're all isomorphic to the standard representation of SO3 and R3. So this is adjoint representation of SU2. So all of them are sort of can be identified with each other. And I'll need sort of an identification between these spaces. So for instance, if you take a traceless symmetric tensor of type S20I, and I take the endomorphism action on, let's say, omega I, then I end up with an anti-self-dual 2 form. And then I'm just going to denote by pi the inverse map. So I convert sort of an anti-self-dual form into a symmetric, traceless symmetric 2 tensor. Okay? What this means is that any 2 tensor now, I can just split it in this way. So I can write F node for the coefficient, or F node for the coefficient of the metric, and I take the traceless bit, I split it into its 3 different bits. And on the other hand, for the self-dual bit, I have a triple of functions, F1, F2, and F3. And the anti-self-dual bit, I can just set it to 0 because it's going to act trivially on the triple. So what this means for us is that any flow of an SU2 structure can now be written in the following way here, where F node corresponds to conformally rescaling your H structure. So this sort of scales the matrix this way. On the other hand, the functions F1, F2, F3 simply correspond to sort of rotating the triple inside its sphere. And on the other hand, the traceless symmetric tensors, or B01, B02, B03, when viewed as anti-self-dual forms, they are just evolving in the anti-self-dual bit of the triple. Okay? And from this, you can, for instance, easily compute how the almost complex structures are going to evolve. So for instance, if you compute that how J1 evolves, then you see that it evolves using sort of F2 and F3, and there's no F note in this because conformal rescaling doesn't affect the almost complex structure at all. And you see this doesn't depend on how omega 1 is evolving. It purely depends on omega 2 and omega 3 because that's what determines the almost complex structures. And you can do the same for the other guys. And now sort of the question is now, if you would like to have a good flow, the question is how do you choose the functions F and this traceless symmetric tensors to be? So what you would like a good flow to have, you would like it to be diffeomorphism invariant, and you would like it to only depend on the SU2 structure. And you would like it to, so you don't want to add external data to what we already have, and you would like it to be second order just because we would like it to use sort of elliptic theory to get existence of a good flow. Okay, so think of something like Ricci flow, where when you evolve sort of the metric by its Ricci curvature. Okay, so the first question is, we want to go to second order quantities, but let's first look at what are the first order quantities that we have. Well, we only have one first order quantity, that's the intrinsic torsion. So remember, the intrinsic torsion is defined by the covariant derivative of the triple, so omega 1, omega 2, omega 3, and it's a one form that lies in the complement of SU2. So, but because the complement of SU2 is the space of self-dual 2 form, that simply means that the intrinsic torsion can be identified with a triple of one forms, A1, A2, and A3. Okay? And from now on, I'm just going to stick with these one forms. For instance, you can very easily compute them. For instance, using the covariant derivative of omega 2, you can compute A1, or you can equivalently compute it using exterior derivative and the almost complex structures. And you can sort of cook up, every sort of natural geometric structure, the geometric sort of definition, you can cook up in this language. So for instance, asking that 2 form is symplectic can be equivalently said as sort of there's some algebraic relation between the AIs and AKs. Similarly, if the almost complex structure vanishes, then this relation has to hold. And if you want both of them to hold, then both of them have to vanish, and so on and so forth. Okay? So I want to think of everything just in terms of the AIs from now on. So next, we'd like to find second order invariants. Now, there's a result due to Robert in his remarks that any second order invariant of an H structure where H induces a metric can be computed from this representational theoretic argument. So here, lambda 1 is simply the space of one forms. S3 here is the space of symmetric 3 tensors. H perp, as usual, is the complement of H inside SO2, so the Lie algebra of that. So I don't want to sort of tell you about this formula, but what I would like to do is I would like to just specialize this formula in the case when H is equal to SU2. So if I do that, and you do the representation theory, this is what you find out. You get the 1 R5 component, 12 R3 component, and 9 copies of R. So, I mean, an SU2 module is completely determined by dimension, so specifying the dimension is all I need to do. Now, by contrast, if you compute the space of second-order invariants associated to SO4, then you get 2 copies of R5 as representation of SO4, 2 copies of R5, 1 copy of R9, and 1 copy of R. Of course, this is just the curvature tensor. So, of course, R here is just a scalar curvature. The R9 is simply the traceless part of Ricci, which as SU2 modules splits into 3 bits. So there's 3 copies of R. And one part of the Weyl curvature trivializes. So I have it trivialized, so I get 5 here. And one stays sort of irreducible, which is the R5 here. Okay, and sort of the conclusion of this computation is that there are certain quantities which are SU2 invariant. So there's a certain SU2 invariant, diffeomorphism invariant quantities, which cannot be computed out of curvature. And there's 6 3-dimensional components and 3 1-dimensional components out of this. So let me make all of this very explicit now. So there are 2 sources of second-order quantities. First, you can look at derivative of the first-order one, or you could look at the new ones, which come from the curvature. The torsion is simply given by a triple of 1 form, so the derivative is simply the derivative of a 1 form. Okay, it's a 2 tensor. On the other hand, the curvature splits into sort of scalar curvature, Ricci, self, and anti-self-dual Weyl. And as SU2 module, I can split it as before. As I said, sort of space of symmetric tensor splits into 3-bit. And on the other hand, Weyl split into 5 irreducible, 5 functions, basically. But there's an overlap between curvature and torsion. So they're not sort of completely independent of each other. And in fact, a sort of a well-known fact is that every sort of second-order invariance can be computed purely using the derivative of the intrinsic torsion and the anti-self-dual part of Weyl. So let me sort of give a proof of this, because it's very sort of simple. Maybe it's not what is the standard proof, but here's how it works. So the intrinsic torsion is defined by this relation here, by this endomorphism relation. So what I can do is I can simply differentiate again. So if I differentiate again, I hit the derivative on the first term. I get some quantity here, the derivative of this guy. I get some quadratic terms in T, and I get the second derivative on the tensor. So if I just Q-symmetrize on the first 2 index, what I simply get is the exterior derivative of the first term, some quadratic term, which I'm going to ignore, and the curvature acting on my original tensor. This is known as a sort of Bianchi identity. Spiro Cariganis called it this way because you can prove that this identity arises due to the diffeomorphism invariance of the torsion tensor, just like with the usual Bianchi identity arises as the diffeomorphism invariance of the curvature. So the sort of key point of this is the following, is because T is determined by a triple of 1 form, what this tells you is basically that the exterior derivative of these AIs will determine Ricci and the self-dual part of Weyl. Okay? So we're looking for second-order invariance. So let's go back to the derivative of the torsion. So you take a covariant derivative of a 1 form. Yes?
Perhaps just mention that the Ricci-Bianchi equation holds in shape of function.
I'll say that at the end. No spoilers. Okay. So if you take the derivative of a 1 form, you get a 2 tensor. So I can split the 2 tensor as SU2 modules. So what do I get? Well, I can always take co-differential of this. So I get the divergence. So I get 3 functions out of this guy. And on the other hand, I can just take the inner product of each of these 2 forms with omega I, omega j, so omega 1, omega 2, omega 3. So I get 9 functions out of this. So I get a total of 12 functions. On the other hand, I can project each of these 1 form into the anti-self-dual bit. And I can also sort of split the symmetric bit into its irreducible components, these 3 components. So this gives me a total of 3 3-dimensional bit and 9 3-dimensional bit. But there are some relations between these guys. Namely, if you swap the indices sort of I and j in this expression here, this is equal to the same guy up to lower order terms. So there's 3 1-dimensional relation. So what this tells you is that, in fact, there's not 12 functions. There's 12 minus 3, so there's 9 functions, and 12 3-dimensional bit and 1 5-dimensional bit, which is precisely what the representational theoretic argument gave you earlier. So effectively, what I've just done, I've just found a basis for the space of second-order invariance. And these are given by these terms here. Okay? So any second-order quantity has to be expressible purely using these guys here. Okay, so you should ask me, like, okay, why do I care about all these guys? Should I? Okay, so I want to convince you that you should. First, you know that the self-dual vowel can be computed using the one-dimensional component. So that means if you trace out, you should be able to compute it. And here's an expression for it. So for instance, the self-dual vowel is a 5-dimensional guy. So this is like a 5-dimensional guy. So here, omega 1 squared simply means omega 1 tensor omega 1. And if you trace out the right way, you should be able to, you will find this formula pops up. Okay, so you see that this is precisely the inner product of these DAIs with omega i's. Okay, and you see all these terms appearing here. And there's lots of sort of obvious, well-known facts that you can deduce from this expression. So for instance, if you work out what happens if the almost complex structure is in fact integrable, then you can check that the second and fourth term in this expression here will vanish. On the other hand, if your manifold is scalar, you can check that everything will vanish except the first one, and in that case, it in fact is scalar curvature. Okay, just from this formula. These are well-known facts that you can deduce from rep theory as well. Okay, but this is like an explicit expression. So here's a formula for the scalar curvature now. So this is precisely the sort of the inner product of these DAIs with omega I. This is the highest order term, and then you have some quadratic term that controls the rest. On the other hand, the traceless part of Ricci is computed using the anti-self-dual part of these DAIs. Okay, so this is. So remember that P1, P2, and P3 are simply the operators that convert an anti-self-dual form into a symmetric tensor. Okay, so these are the three independent components, and they are all computable simply from the exterior derivative of this AI, the anti-self-dual bit of it. But note that we have not seen neither divergence nor these other sort of traceless symmetric projection of the covariant derivative. That's precisely because these were not sort of curvature terms. That's why we haven't seen them. So let's try to find a way to find these guys. So a good way to find sort of second order quantity is to look at some sort of quadratic functional involved in the first order one, so in terms of intrinsic torsion. And so there's these natural functionals that you can consider. For instance, you can consider the inner product of A1 with itself, or with other guys, with A1 and A2, or you can plug in here also the almost complex structure. So you can use them as sort of building blocks for quadratic functionals in the torsion. And if some of them which are of particular interest is, for instance, like the intrinsic torsion of your SU2 structure can, for instance, be computed using, this is just the norm square of the A1, A2, A3. So for instance, if you're interested in the Ninhighest tensor of, let's say, J1, then you can look at this L2 functional associated to it, and similarly for the omega 1. So let me give you some first variation formula. So if you look at the first variation formula of A1 squared, then you see this term here popping up. So I've split everything in terms of its irreducible component. So you see in the metric bit, you see some inner product of A1, dA1 with omega 1. So you see some sort of scalar curvature, vowel curvature type term. And in the P1 bit, you see some sort of Ricci, traceless Ricci type term. And on the other hand, now you see that these new terms here start to pop up. So this S20, the projection of the Nablat's A's into this symmetric bits start to pop up. And you see that this occurs in the P2 component. This guy occurs in the sort of S203 component. And in the skew bit, you see the divergence pops up. And you get similar sort of expression for this inner product here, which is a bit more complicated, but this is what it is, plus lower order terms. Okay? I'm only looking at the highest order term in this expression. The point being here is that everything occurs, and in fact, you can swap between different guys. So for instance, like an anti-self-dual form is being considered as a symmetric tensor, and for instance, this guy here, which is a symmetric 3-0 tensor, is being viewed as an S202 tensor. Okay, so there's some sort of permutation going on between the different R3 modules. Okay, this one's another one, which is a bit more complicated. Okay, so but what we're interested in today is probably the most natural functional is the one which sort of minimizes the L2 norm of the intrinsic torsion. So if you compute the critical points of this guy, you find out that these are given by this term here. So let me go with the C bit first, the skew symmetric bit. So the skew symmetric bit is simply the divergence of these one forms, the co-differential of them. On the other hand, the symmetric bit, this is what you get. And this is an exact expression. Okay, this is not up to highest order term. The lower order terms are right here. So this is the norm square of the torsion, and then you have some sort of pairing of the torsion with itself, some quadratic terms in terms of the torsion, and everything else is some sort of second order quantity. One thing I should point out is that if you look at the first column here, this is precisely Ricci term. So you have Ricci term here, plus some other other guy here. So there's sort of one thing I should point out. Okay, cool. Okay, so this is the first variation formula. Okay, so what were we sort of trying to do to begin with? So we were interested to look at flows of SU2 structures, and we wanted flows to be sort of second order, so we classified all possible second order quantities, and we actually showed that they occur in sort of natural problems. So if you wanted to find some, if you were interested in a certain problem, you can just set up a functional, look at this critical point, and then you will get some second order terms, and hopefully you can use that to flow. So what this means for us is that whenever you have a flow of an SU2 structures, and you have these functions f0 up to f3 that you have to choose, and these traceless symmetric tensors, there's only a finite pool where you can pick them from. And this has to be precisely in this set here. The function can only be divergent in these inner product terms. And the symmetric tensors have to be part of this sort of the projection of these nabla AIs and the anti-self dual bit. Note that you can't use anti-self dual as the anti-self dual part of Weil because this lives in a 5-dimensional representation, which doesn't occur in this flow here, because these are just two forms. Okay, so now, okay, these are all flows have to be of this form. So now the next question is, well, which of them have short-term existence? Because that's what we need. So probably the sort of simplest flow is the harmonic or isometric flow. So in this setup, what you do is you look at this variation of this guy here, which I told you earlier, but you fix the metric and you just vary the triple. And if you do that, then the flow that comes up is the so-called isometric or harmonic flow, which in this setup just tells you that all you have to do is you can only rotate the triple around by this Q-symmetric 3x3 matrix. Okay? Sorry. Okay? And in the sort of 3-dimensional setup, observe that you will be a harmonic SU2 structure precisely if all these guys here are harmonic, which is another way of saying that the induced Levi-Shifter connection on the space of self-dual 2 form is in fact in Coulomb gauge. This is, in Coulomb gauge is precisely how you, the way you define Coulomb gauge is you try to minimize the L2 norm of connection. So this sort of makes sense, it's precisely what it is. And the point here is that divergence of torsion is only a gauge fixing condition, which is precisely what's going on. And the fact that this flow has short-term existence is part of sort of the general theory that Eric Lobo and Enrique Sepp developed. So they prove short-term existence and uniqueness. And together with the work of Daniel Fadel and Andres Moreno, they prove conditions when you have long-term existence. So for instance, if the torsion is small enough, you could prove that. You have compactness result for these flows. You also have sheet-type estimates. And this, again, holds for general A structures. This has nothing to do with SU2. So in particular, we can get all these results from here. Okay.
What's your definition of Coulomb gauge?
That, well, let's say that it's harmonic. Let's just
Curvature is divergence free.
Yeah, curvature. Curvature is divergence free.
But that's not,
There.
that's a curvature condition on a, you need the gauge fixing condition, right? So there's
Yes.
no gauge in a statement about curvature.
You think of the A1, A2, A3 as being the co-differential of the connection is vanishes. I'm thinking of the A1, A2, A3 as being the connection.
In physics, Coulomb gauge means that the divergence of the connection is 0.
It's the divergence of the connection.
Okay.
Okay. How am I doing on time right now? I have like.
Sorry, I said curvature, I meant connection. Otherwise it's
Yes,
Have,
between 5 and 10 minutes.
I have 10 minutes. Oh, okay. Let me. Yes, go for it. Yeah, under certain assumptions. Now, yeah, if you, yeah.
So to set this up, you also already have a topological condition. You're assuming that lambda plus is trivial.
Yes.
Which is the same as saying it's a spin manifold. If it's compact form manifold, it has to be spin, and it has to have twice the other characteristic plus 3 times the signature. It has to vanish.
Yeah. I already. Okay, so I'm gonna, since I'm sort of running out of time, I'm gonna skip the next slide.
Yeah. There's no rush, Udhav.
Okay, no. Let me go for the main result that we have. Okay, okay. So the main result that we have is that if you evolve an SU2 triple, such that on the symmetric bit you add minus twice Ricci, so this is a Ricci flow, and I'm going to add to that a Lie derivative term, and the Lie derivative term is going to be by some vector field V, which is coming from the intrinsic torsion. This is sort of J1A1 plus J2A2 plus J3A3. So this is a symmetric bit, and on the other hand, on the skew-symmetric bit, I just put the same thing as I had before, the divergence condition. If I couple these two equations, and I put in some parameter, which I'm going to call mu and lambda, then there is two sort of case of particular interest. Observe that if I set lambda here to 0, all I'm doing is I'm just coupling the Ricci flow with the harmonic flow. On the other hand, if I set this constant lambda here to be -1, then it turns out that this is precisely the negative gradient flow of the L2 norm of the intrinsic torsion. Okay, so there's two very nice flows inside this parameter of guys I'm looking. And I'm only going to look at highest order term. Okay, so dot, dot, dot here means sort of lower order term. I'm just going to ignore these guys. And our main result for the time being says that if the difference between this mu and lambda lies in a certain range, like so sort of, 0.1 is not an exact value, it's like some decimal thing, but I've just approximated that. If it lies between a certain range of values, then the above flow will have short-time existence and uniqueness. And one sort of reason why you might believe such a result should hold is because I'm starting with Ricci flow, which is parabolic, modulo diffeomorphism, and on the other hand, I'm adding to that on the skew-symmetric bit the isometric flow, which is also parabolic, and both exist, so it's reasonable to believe that the combination of both of them might exist, okay? Now, of course, in the isometric case, the metric is fixed, but now I'm evolving it by Ricci, so it's not obvious, but it is true. So here's a quick sort of sketch proof of this. So, of course, the flow is not parabolic because I've used diffeomorphism invariant quantities, but because of that, that means that you should think of that, you should try to use the Turk trick to prove short-term existence, which is precisely what you do. So you replace the second order operator that you had on the right-hand side by a Lie derivative term. So I add to this Lie derivative term where W dt is simply the de Turk vector field, where you put what was that you use to prove short-term existence of the Ricci flow, and I add to it precisely the other vector fields that I had before. So if you do that, and you compute the new flow, what you end up finding is that the symmetric bit now becomes the Ricci flow plus the Lie derivative of the de Turk bit, and as compensation, the vector field, the exterior derivative of this vector field here now pops up in the skew-symmetric bit. But the upshot of this is that now on the symmetric bit, I have precisely Ricci de Turk flow, and at the expense of that, I have some worse terms that I have to introduce in the skew-symmetric bit. So if you linearize this whole operator, and you check the condition where the principal symbol is invertible, then you get the precise range. This is precisely how you prove that. So you get a solution to your original flow simply by pulling back by the diffeomorphism generated by this vector field here. Okay? And for uniqueness, you can essentially argue in a very similar fashion as in the case of Ricci flow. So what you do is, suppose you have two different solutions, you can pull back by the diffeomorphism generated by this vector field a priori different, sort of V1 and V2, you pull that back. Now the new flow you get will satisfy some sort of Ricci flow, by which I mean that on the symmetric bit, it's going to have some Ricci term. And then you can use the harmonic Mach flow to cook up two new diffeomorphisms. Once you have the diffeomorphism, you can pull back again, and the flow is going to essentially end up looking a bit like this flow, this Ricci de Turk vector field plus this guy here. But this flow here is parabolic. So it has short-term existence and uniqueness. And then essentially what you do is you pull back by the diffeomorphism you get to essentially extract off uniqueness for the original flow. And this is how you sort of do it in the case of Ricci flow. This is roughly the argument. Okay, well, I've considered a very specific type flow before, but what about more general flows? But now the thing is that there's lots of choices. So every time I add, if you notice, in the beginning, the second order operator didn't have any Weyl curvature term. So let me add in some Weyl curvature term now. So if I add in, for instance, to the previous operator, this term here in terms of the matrix, so this is a Weyl curvature term, and I multiply it by some constant, then you will find out that if you do the computations, that this flow here will have short-time existence precisely when this constant here is sufficiently small, and also it will make the range of values for which the flow works a bit smaller. I mean, the value sort of 0.3 and sort of 9 was just some values that worked, but I didn't try to sort of optimize the range. But the point being is that as soon as I add in Weyl, the set of values for which the flow works will go down. So the more val I add, the worse the flow gets. That's precisely because Ricci behaves like Laplacian, but val doesn't. So for instance, if you linearize this operator and you compute the principal symbol, you see there's no sign that arises in this term here. That's basically what happens. So I have to always estimate it. On the other hand, for the other terms, it depends. So for instance, if I look at the linearization of the divergence of A1, you'll see that there's a term that pops up that has a sign on the coefficient of F1. So basically what that means is that if I put this div A1 terms in front of omega 1, and I sort of look at that flow, it will tend to make the flow more elliptic because this will give me a sign. This will give me sort of a positive sign, and then I have to estimate the bad terms, which in principle I can kill using the Turk. Similarly, for this guy here, it also comes with a sign, but that, I mean, the reason why it comes with a sign, you can think, because this comes from Ricci, so it had to come with a sign. So you can, again, do this thing. But the problem here is because you have several modules of dimension 1 and several modules of dimension 3. So it matters where you start to put everything, okay? So naturally from this, you can also prove short-term existence of this more general flow, where in addition to the thing before, I add any sort of type of lead derivative terms. And provided that these constants are sufficiently small, I will again have short-term existence. That's simply because invertible is an open condition. If I'm close enough to something invertible, it will still work out, fine, provided it's small enough. OK, so let me sort of, in the last few minutes probably that I have, how much of what I said is actually dependent on SU2? Maybe you don't care about SU2, maybe you care about G2 or spin 7. So how much of what I said actually depends on what I did? So if we go back to the beginning to Berger's list, you can always define the intrinsic torsion from this relation here. Okay, take the derivative of your tensor, and then that precisely is the torsion. But then you can always compute the space of second-order invariants. In the G2 case, if you look at Robert's remark, you'll find out that the space of second-order invariants has 1 copy of R, 3 copies of traceless symmetric tensor, and 2 copies of R7. I mean, sorry, I'm intersetting this with the space of tensor. So basically, I'm looking at all the possible second-order invariants, and I'm looking at all those terms that I could make into a tensor. And this is what I get. You can check remarks to find that out. Today, I did this case, and I explicitly computed all the second-order terms for this guy here. You can do it for other cases. For instance, if you do it in SP2, you get this space here. So here, the Lie algebra of SP. The Lie algebra of SP2 arises in the space of traceless symmetric tensors, and this R5 here is the standard representation of SO5 and R5, which arise in H-perp. You can go ahead and do it in the spin 7 case as well. It gets slightly simpler. There's slightly fewer terms. Once you do that, well, you can use, again, the Bianchi identity to cook up a good basis out of this. Again, this Bianchi identity had nothing to do with SU2, as Enrique pointed out before. You can always use this. There's nothing wrong. And then you can, again, cook up any flow from a chosen basis from this set of pools of endomorphisms that you can cook up naturally from your geometric structure. And then, again, you can use the same argument because as the Ricci-Deter tricks that I use, because, again, this has nothing to do. I mean, I had to use the linearization of the second-order term, but in principle, you can do that for whatever term you have and still go ahead and do the computation. And indeed, the G2 case sort of recently appeared in a paper by Duvedi, Ganotis, and Karagiannis at the end of last year, which is sort of what sort of motivated us to do this. And in their case, they also prove that the negative gradient for the L2 norm of the intrinsic torsion of the G2 structure has short-term existence, and also they prove that the rich harmonic flow exists. So this could a priori be a much more general phenomenon, okay, than just sort of, I mean, although they stick very much in the G2 case, if you look at the paper very closely, you'll see that everything has analog, and you can extend everything in that language here. Okay. Sort of a point of last remark sort of is that if you look at the space of second-order invariants, there's always a minimum set of candidates that you will always find. Okay, you will always find scalar curvature, so you always have a copy of R. You'll always have Ricci sitting in there, so there's always going to be sort of S20 sitting inside the space of second-order invariants, and you will also always have H-perp. So you always have divergence of the torsion. The other symmetric tensor that occurs in this space comes from the fact that the space of torsion tensor always has a 1 form sitting in there. And that 1 form, you can use that to compute lead derivative of the matrix. So that's going to feed in one more guy. And in fact, these are always going to be present. So you can see in all these cases, this guy here is always present. Okay? So it's only the other terms that you actually need the H structure to figure out what are the other extra terms that could potentially occur. Okay, so does that mean that we've classified all flows? Well, not really. We still have to work out the details for the other H structures, sort of find out what are the quantities. So I've introduced two new set of flows. One is sort of the Ricci coupled with harmonic flow, and the other one is the gradient flow of the negative gradient flow of the intrinsic torsion. All I've done is I've only looked at highest order term to prove sort of short-time existence and uniqueness. But we don't know anything about sort of long-time existence. We don't have sheet-type estimates. What are the singularities? What are solitons? We don't know. I mean, we still haven't done anything about that. Are there other sort of interesting flows? So for instance, if we wanted good critical points, you'll have to fix the lower order terms. Because just like in sort of the Laplacian curve flow, we added some other second order term to get short-time existence, but then you lost critical point. Now, if we have sort of short-time existence using highest order term, can we add some lower order term to get sort of good critical points? Can we do that? We don't know. Maybe we can look at sort of things which are quadratic in terms of the intrinsic torsions. That would be sort of a good way to start. Another question is, are the sort of first order conditions that you can check would be preserved? So for instance, in the Laplacian flow, you start off with the closed condition, and then you prove that, and then once you, if you just look at the Laplacian flow without the closed condition, that would not exist typically, okay? So you need the closed condition to be there. Like, can you prove something analog in the other case of other H structures? So if you have some first order condition, that would be preserved. And then, of course, we've used sort of very elementary techniques to prove short-time existence. Can we use sort of more sophisticated techniques to get short-time existence as in the Laplacian flow? And also sort of an interesting question would be that, if once you impose close, in fact, you can check that the only second order quantities that you have, which would be a symmetric tensor, is only Ricci. So basically, any flow of a closed G2 structure would have to sort of induce Ricci up to sort of at the level of the metric. There was no choice to begin with. Can you prove something like that in the case of other structures? Like, can you have some constraint on torsion that hopefully would tell you that any flow that preserves this quantity would have to induce Ricci? That would be a good candidate to introduce. Okay, so this is my last slide. So thanks for listening.